Okay, welcome to class. And this is Introduction to Deep Learning. A Happy New Year to everyone. Happy to see many of you come back. We left off last year at the end of this chapter on convolutional networks, in particular looking at this ImageNet benchmark challenge that has been driving a lot of the deep learning revolution. The aim of recognizing objects in images, and you can see how the performance over the year got better and better. In particular, with this marked the breakthrough of convolutional networks, where you have lots of layers of convolutions alternating with nonlinearity activations, and we see with the networks getting deeper and deeper, more and more layers, and the performance getting better and better. And one of the challenges was how to make sure that you can make the networks deeper, how you avoid this vanishing gradient issue that you often run into when you have too many layers and you try to learn the parameters by backpropagation learning. You multiply derivatives at every layer, and once you multiply small numbers, you risk in them getting zero with hundreds of layers. And the challenge was how to make sure that you can have things like 152 layers here. But you saw that, whereas the depths of the networks went up, the accuracy got better. Now, talking about convolutional networks, I wanted to add one aspect on what's called fully convolutional networks. And this is the idea here is as follows. We have this standard classification network that we've been talking about, where you have different kinds of convolutional filters, and we saw there's works that analyzed what kinds of convolutions, how should I stack them, what size of convolutions do I run at every layer, etc. But in the end, we would always have a fully connected layer. And this fully connected layer was necessary because you wanted to have a classification out and you had a very high dimensional input. And so you ran this fully connected layer, one or maybe even multiple fully connected layers. The problem was often that most of the parameters, most of the network capacity was in this fully connected layers in the end, because the convolutions, they're very compact. You have a small filter kernel that you basically slide over the image and you apply the exact same filter everywhere. So you only have a handful of parameters for each convolutional kernel, right? Whereas the fully connected layers, they have tons of parameters. If the input is large, they need a lot of parameters. The other issue is that these classification networks, they typically require a fixed size input. You see it here, 227 by 227. Well, in practice, you want something that works on any resolution image. You don't want to be limited to a specific choice of resolution. Obviously, you can always take your input and downsample it or squeeze it to the required resolution and shrink it or whatever. Right, but then you might need to change the aspect ratio, etc. So this is not desirable. The other aspect is very often in many application tasks, we don't want classification. We don't want to just say cat, no cat, dog, whatever. We may want to do something else with the image. For example, maybe segment it, tell me what am I looking at, is what pixel is part of the cat, what pixel is part of the background, etc. And then the output will not be just a classification, but you want an output that potentially has the same resolution as the input image. Let me close the door here. Otherwise, you guys will freeze to death. Yeah, and this leads to what's called fully convolutional networks. And we'll look at how that works. So by the way, in these pictures, the activations, we've omitted them. So this is just the convolutions. In practice, you always have nonlinear activations in the middle. And we already talked about these one-by-one convolutions, which basically compress the output. before you process it. This is one way of reducing the capacity of subsequent layers, right? But what you can also do is you can apply just convolutions all the way through. And then once you apply just convolutional filters, since these are being slid over the image, it doesn't really matter how many pixels your image has, right? A convolutional filter you can run on any resolution image, right? So that's, if you don't have any fully connected layers, then it's easier. Then you can run it on any image, and then the output will also be an image, as we saw with convolutions, right? But in practice, you might want to have a fully convolutional network like the one that was advocated by Long and Shellhammer in 2015. This introduced this fully convolutional net. And one of the challenges they wanted to tackle is semantic segmentation. And here the idea was, given an image, can you put out an image that actually labels every pixel as to what is cat, what is dog, what is whatever else, right? And the way they tackled it, it was with convolutions. And as we saw, you can apply a sequence of convolutions, and then you typically, you get images that are smaller and smaller in spatial resolution, but they have more and more depth channels, right? The question then is, you see it here, once we have kind of condensed all the information in this convolutional processing, how do we get back to the original resolution image? Right? Because the convolutions, there was in the process there is a downsampling happening, and so we need to upsample back to the original resolution. And this is something that we can look at in more detail. How can we do this upsampling? So if you have, for example, an input like this, you want to upsample it to a higher resolution, right? You have to imagine that we created this downsampled version in the convolutional filtering and pooling, right? The pooling is the step that reduced the resolution and aggregated information in a neighborhood. But then you want to get back to the original resolution, which means you take the original image and then you have to upsample it. This is what it's called. And you can do that in many ways. And what you have to ask is, what is the color that you should assign to the pixels in between? And there are many ways to do that. One standard technique for upsampling an image is interpolation. This is something you might be familiar with, a very classical idea in image analysis, something that all, softwares for visualizing images always do. If you take an image and you want to see it on your screen and the image has only 100 by 100 pixels, then that image would be super tiny. So for you to see it, the system has to upsample. And so upsampling is always being done in one way or another in cameras, in computers, etc. Standard procedure. The most simple upsampling or interpolation technique is called the nearest neighbor interpolation. It basically means on this grid, we just go to each point here and take the color of the nearest neighbor. So let's say this point will, these points may take color from this blue one here, right? Whatever is the nearest pixel, you take that color, you fill it in, and then you get this typical blocking artifacts, right? You see the pixels of the original input image. If you don't like that, you can go to what's called a bilinear interpolation or a bicubic interpolation, which means you interpolate the neighboring colors with varying degrees of sophistication. So this is what you can do here, and that gives you these kind of more blurry upsamplings. Sorry. This is nice. It creates few artifacts. It mostly creates a certain blurring. But obviously, you can also do that with what's called a convolution, or more specifically, what's called a transposed convolution. This is something that was done in this paper. This is a paper from the team in Freiburg. Thomas Brox is a former postdoc of mine who is now a professor in Freiburg, and he they proposed this transpose convolution to basically get from an original low resolution to a higher resolution one, and this they treat that as a convolution, and basically they can learn the parameters. And so the way you can see that is visualized here. Let's say you have an input 3 by 3, the blue 3 by 3 grid here, and then you run a convolution filter where you basically do a weighted sum of whatever is in here to create, in this case, a 5 by 5 output. And you can learn the parameters of this convolution, and that's the idea. So much like the convolution, this transpose convolution is a filter that can also be learned in a neural network. So this is called up convolution. Don't confuse it with deconvolution. Deconvolution is something different. But here this is called up convolution. Deconvolution is when you do a convolution and you want to invert the effect of that convolution. This is called deconvolution. It's a different problem. Here it's really a convolution that increases the resolution of your input. And if you do that in a cascade of unpooling and convolution operations, then you get what's called an encoder-decoder architecture. We'll talk about that a little bit later. And what we'll talk about now is a network that has become extremely popular also by the team of Thomas Brox and collaborators in Freiburg. It's a network called the U-Net. And what that does is it starts with the original input image on the top left. And then it does this standard convolutional filtering pipeline that we've seen to get a structure that has much lower resolution, but much more channels, as you see here, for example, 512 channels or something like that, right? But a much smaller resolution here. And then there is this, and that's why it's called U-Net, because it, you know, if you visualize it in this fashion, it has the shape of a U. Because then what happens is that you have up convolutions here that go back to the original size of the image of the input, same resolution as the input. But the clever thing is that you have what's called skip connections here. So you combine the upsampled version from down here with the original version that you append here, right? So you get even more channels, and the white block is always basically copy pasted over from the same resolution there. And that means in the output looks at the various coarsened versions that extract the semantic information, but it also looks at the same resolution input. And so it gives you access to both the downsampled feature maps, but also the features from the original resolution. That's the idea here. And as you can see, there are two components. There is this left branch of the U-Net. This is called the encoder. And then the right branch of the U-Net is called the decoder. And so if we look at this left side, the left branch of the U-Net, this encoder, it has this what's called contraction path or encoder path, where you lower the resolution and get with convolutions and max pooling, always 2 by 2 max pooling with a stride of 2 that downsamples the image, and then so you get something that has much lower height and width, so spatial resolution is lower, but the depth of the structure is higher. By the way, I have worked with Thomas Brox for many years. He was my first postdoc, and for me, this work is not very surprising somehow in the structure. Thomas Brock's, his real background when he did his PhD, he worked a lot on optical flow estimation, and in processing videos to extract flow, one of the most important aspects is this coarse to fine processing. And this is very, very much ingrained in this neural network architecture here, that you have this coarsening that you do on the encoder stage. So in a way, if you know a researcher, sometimes you can almost predict what they're going to do next and anticipate and see how all things come together. This is the left branch here, this encoder branch of the unit. On the right branch, this is the upsampling, so the decoder branch, where you decode back into the original resolution. And this is sometimes called the expansion path. And here you have a combination of upsampling, up convolutions with learnable parameters, right? But also these skip connections that allow you to basically copy over from the left branch. And so the decoder, at every step it increases the resolution, the spatial resolution, but it reduces the depths again. And so this UNet is one of the most popular networks for image segmentation. It was proposed for medical image segmentation. Here you see biomedical image segmentation. This is the work that Olaf Ronneberger was very keen on at the time he worked in this biomedical image analysis field. So that's why they published it there, but it's been used a lot also in other segmentation challenges. And I think it's probably the most popular segmentation network to date. Here's a few more references about convolutional networks and also these fully convolutional networks and the unit. That brings me to the next part. This is the part that will mainly cover recurrent neural networks, RNNs, and transformers. So in this lecture, we learn a lot about new architectures, not just the UNet, encoder-decoder networks, but also transformers and RNNs. This is something I'm sure many of you have heard of and have tried. I guess everyone has tried ChatGPT. This is an example of a transformer architecture, and that's really revolutionized language analysis, but also many other domains in the wake of it. But before we go into RNNs and transformers, let's first talk about transfer learning. A short part about transfer learning. What is transfer learning? Just so you've heard these terms. Here's the ResNet that we've talked about. One of the issues with these networks, and you see it almost from the picture, is these networks have gazillions of parameters. For example, ResNet 152 has 60 million parameters. To learn all of these parameters by backprop learning, is very computationally demanding. And so it can take many weeks and lots of GPU resources to train it. And sometimes training big networks can take hundreds of thousands of dollars. So something that even for big companies gets to be very costly. And so the question is, whenever I need to solve a problem, if I want to solve it well, do I need to retrain a whole thing from scratch and invest hundreds of thousands of dollars and also energy resources, right? That's a big issue. And so what people often do is they tackle their challenges with the concept of transfer learning. And the idea of transfer learning is that you already start with a pre-trained network. So you've trained a network to solve a specific task, let's say ImageNet, and then you want to see if you can recycle that network to do a different task. And this is called transfer learning. And it comes into play when, training your own model is maybe too expensive. Maybe you don't have the same number of GPUs that Google, Meta, or other companies have. Most likely you won't. Who does, right? Or you don't have the training data to do it, right? Sometimes you have a specific task, but whereas in ImageNet you have 14 million images, maybe on your task you only have a few thousand images. And then you cannot train a network with a gigantic capacity if you don't have the training data to actually make it work. And so then you can revert and try to recycle, reuse a pre-trained model and basically fine-tune it. And the idea is, and this is a lot of work that went into this field, that you have some distribution of data, P1, and a different distribution, P2. P1 is the data that someone had, like ImageNet, and they trained their network to solve it, the ResNet 152, right? But then you have a small data set that has a different distribution, P2, and you want to somehow adapt your big network to this new task. But you want to make use of what has been learned on the previous task. And this sort of makes sense, right? If you think about humans going through the world, they have seen a lot of things, and even if you get a new task, someone trains you to distinguish two different patterns, you can quickly do it, maybe because you've seen similar other patterns in other challenges. And so I think the human brain, to a large extent, does that. And in fact, these features that we observe in a convolutional network, they are very much also observable in the brain, in the visual pathway, right? And so the idea here would be that you've trained a network, and then you can maybe recycle the low-level features without having to retrain the whole network. You just basically freeze them. Right? And that means if you look at this, this is now processing from bottom to top. Bottom is the input image in blue. And then you have a stack of, as we've seen, convolution and max pooling operations in alternation, right? And then in the end, fully connected layers. And as we discussed, these first convolutional branches, they do feature extraction. And then the fully connected layers, they basically compute the classification. And if you look at the feature extraction, you would expect that at the low levels, at the earlier layers, the system extracts information about edges in the image. Where do I have edges in different orientation? Then in the mid-level, I will extract some more higher level geometrical features like circular structures, ellipsoidal structures, things like that. And then on the higher level, I will actually have, I will be able to extract information about wheels or windows or more sophisticated geometric structures, right? And then these are the decision layers, the fully connected layers. And then when you tackle this as a transfer learning problem, there are many ways to go about this, and this has been discussed in a number of papers. The idea is that you only modify the decision layers, so you keep the whole feature extraction pipeline, but then you have a different task and you can fine-tune the fully connected layers only. And so basically you train, for example, only the very last fully connected layer, keeping all the other ones fixed. And so in the lingo of machine learning, you would say you keep the rest frozen and you just learn the final layer. Or you can learn the last 3 layers and keep the rest frozen, right? So you train that one and keep this one frozen. How much you retrain depends, right? Depends on how much compute you have. Depends on how many training samples you have. If you have a lot of training data and a lot of compute, and all the money in the world, then you can train the whole network. And if not, you maybe start by training just the very last layer or the last 2 layers or the last 3 layers, right? And so that depends, and there's obviously a trade-off that you will reach. The more you train, the better the performance. That's what you can expect, right? But the less you train, the cheaper, the faster you get a solution and the faster you can go to market with your solution, right? So, you have to see what makes sense. And you can do it in a much more sophisticated way, right? You can, for example, train the last layers with a high learning rate and the early layers with a much lower learning rate. Saying, yeah, you can adapt the early layers, but not so much, keep them, because they were pretty good for the previous task. And so you would have different learning rates, and have more evolution on the last layers and less on the early. Or you can add regularization and train the whole network, but say the weights for the early layers should preferably stay where they are, right? Because I don't want to lose the features that I've already extracted. And so you would add a regularizer saying the weights in the early layers should be close to the ones that we had. So there's many ways to do that and to, in that sense, fine-tune the whole network to the new task. When does this make sense? Well, it makes sense when the task T1 and T2 have the same input. That's important, right? Because here I get an image in. And it has a certain, input. If I have a completely different input, then it doesn't make sense to use that network as a backbone and to fine tune it. So you should have the same input, for example, an image, right? It also makes sense when you have a lot of data for the task T1 and much less for the task T2. For example, T1 may be general images from the internet. That's always cheap. Unless you care about licensing, then maybe not, right? But then in certain applications, let's say medical, right, getting images can be very costly. If you have to put someone in a CT scanner for every image you want, that's very costly and not very pleasant necessarily. So it's not as cheap to get. And then it might make sense to use a pre-trained network and do transfer learning. And very often it makes sense if the low-level features that work for task 1 could be useful to learn the task T2. Question is always, how do you know, right? This is sometimes you can only find out by trying. But it's very popular and it allows the whole computer vision and machine learning community to build up on some of the pre-trained networks that are out there. And there's a lot out there by now. Many of the pre-trained networks that people build up on were developed and published by big corporations that had the money to train something like Stable Diffusion or something like a large language model, right? GPT. You don't want to, as a student, try to train from scratch your own GPT. That's just too costly, right? So you need big GPUs, you need big corporations to drive that effort. But once the model is out there, be it an LLM, be it Stable Diffusion, or there was a model for segmentation called Segment Anything, SAM, and that's out there, and then you can fine-tune it to your task. And part of the success of deep networks and the whole revolution there hinges on the fact that that actually works, that you can take a pre-trained network and just fine-tune it to a new task and it will do a fairly good job. And there is always a trade-off, even for big corporations. Do I just fine-tune an existing network or do I train from scratch? And even big corporations don't like training things from scratch because it costs hundreds of thousands of dollars to do it. There is a particular way of transfer learning, that is representation learning. It's kind of related to it. It's a slightly different idea, but similar. The idea of transfer learning was that I have trained a network on task 1 and now I want to train it on task 2. Representation learning is slightly different. It says, can I not train a general network without a specific task? And then use that and fine-tune it to my task later on. And this is called representation learning. And And so the idea of representation learning is that I try to train a network to extract features that are potentially useful for whatever task. So it's in a way trained without any specific task in mind. That's the idea. And the idea is that it allows for discovery of representations required for all sorts of tasks. So I train it to extract features, and then afterwards I look at what is the task. And so this idea is that you have an input X and you train a network to map it to some output Y, and that output Y is ideally then useful. Much like here you see the low-level features are edges. This comes from a trained network, right? But in principle you can try to generate that without a specific task in mind. And the way you do that is that you basically determine what you want in your features, and in particular what invariances your feature extractor should have. You can start with a set of images, for example, and just basically take different images and say when are two images the same, here the cat for example, and then you want the feature extractor to somehow extract features such that they are similar. So basically teaching machines to distinguish between similar and dissimilar things is a little bit related to data augmentation. You can take your data set, you can augment it and say, I want the features to be invariant to these augmentations. Shifting, rotation, scaling, contrast, transform. And so even without having a specific task in mind, I can say the features should be invariant to these transformations. And so you take an original image from your data set, you do a data augmentation, for example, cropping, shearing, rotating, scaling, whatever you want. And then you train a base encoder, this is the green structure, to extract a representation that you see in the middle, H. And the way you do it is you basically pipe this through what's called a projection head that has dense and ReLU, and then dense again. And then you want to maximize similarity if the two crops come from the same object. And if not, then they should not be similar, basically. Right? And then the idea is, so this is trained, and all you have is one image, and you augment and say the features should be such that, that I have similarity in the encoding, so that the representations are similar if the images are taken from the same object. And then you basically throw in your application, you throw away the projection head and you just fine-tune. So it's a little bit like representation, like what we saw earlier, the transfer learning, except that the original task, this maximizing similarity, is just a pseudo task. It's not really what you'd want. It's just something to enforce a reasonable encoding. And it's been shown that this can be made to work. And then you can take this representation and fine-tune it to all sorts of tasks. Detection, classification, segmentation, whatever you want. And it was shown that this is a method that was called SimClear, and there's different alternatives, but these were shown to generate similar performance on the ImageNet challenge. So you can basically train a representation without a specific task in mind. Maybe a few more words. So transfer learning is, I would say, something very useful, that you take an existing network and fine-tune it to a new task. The representation learning can be shown to work, but I believe it's often a little bit more delicate to make it work properly in practice. both representation learning and contrastive learning are a little bit delicate to make work. And one of the reasons is that you want to maximize similarity here of the feature descriptor, but obviously you don't want to get a degenerate descriptor, which is the same for any input, because then you have maximal similarity if the feature is always the same. So you want to also assure diversity. You want to make sure that if the images are from a dog and a cat, that they are dissimilar so that you can later on actually distinguish them. And how to assure that is a little bit challenging without a specific task in mind. So it's much like, teaching children something. If they don't have a task, then they will not learn as well. Learning is always more stably done if you have a task. Now I come to the main part of this section. This is recurrent neural networks. This is a very important topic, and it relates to processing. It was started in the field of processing time series data or sequential data. Data like language, where you have a specific ordering of words and where the meaning of a word will depend on all the words that were before it, etc. And so it's all about processing sequential data. Interestingly, recurrent neural networks emerged on processing sequential and time series data, but the algorithms that came out, in particular the transformers, are extremely successfully deployed also on images that have no natural sequential order, right? So this is interesting. This is often the case that a lot of the innovations in deep learning emerged either on studying and processing images or language. That's the two main drivers of this machine learning revolution. And sometimes you see techniques that were deployed on images can be applied on language, and sometimes techniques that emerged on language can be applied successfully to images. And this is the case here as well. So a recurrent neural network, the neural networks, they process sequence data, and the idea is that both the input to the network is a sequence, but also the output is or can be a sequence. And there's lots of different settings that you can consider, and these are all very relevant and all have different applications. For example, if it's a one-to-one, meaning I don't actually have a temporal sequence, just one input and one output, this is a classical image segmentation, image classification. That's what we've been mostly talking about in the lecture so far. That's the classical neural networks for classification. But then we can have one-to-many. For example, if you have the task of what's called image captioning. You are given one image and you're supposed to say what's in the image. And in a real image, there will be not just one cat and one dog, but there will be lots of objects, right? And so you can have a sequence of objects and like a cat, a dog, a house, whatever, a lawn, right? And the number of objects that you can have in the given input image can be arbitrary. So the sequence can get very long if I have lots of objects in an image, right? And so, I'm just giving image captioning as one example where the input is a single time step and the output is multiple instances, basically. But you can also have the converse. You can have a sequence as an input and a single output. For example, language recognition. In goes a sentence and out comes a classification, whether this is German, English, French, or whatever, right? So this is a many-to-one mapping, basically. And then you will have a hidden state that can have many or it can also have just one, depending on how you do it. And then you can have many-to-many. This is the classical challenge of machine translation. In goes a sentence in Chinese and out comes in English or Japanese or whatever, right? And here, again, the number of let's say, words that go in can be different from the number of words that come out. Obviously, for example, if you take an English sentence, typically I think it will have fewer words than a German sentence. That tends to be kind of long always. Or many-to-many event classification is an example where in goes a video and out comes a classification of what's happening in the video. This is a very important task where people want to annotate videos. Someone like cooking videos, right? First someone breaks the egg, then they heat the butter in the pan, etc., etc. And so then the input would be a set of images and the output would be a storytelling of what's happening in the video. And for all of these tasks where I process sequential data, either in the input or in the output or both, recurrent neural networks are the way to tackle this. And in all of these applications, in at least most of them that come to mind, the sequence is a temporal sequence. So the axis that you have on the x-axis is typically time. But not always. It doesn't have to be time. It can also be space. If you consider images, then you can also have space where you have different parts of an image and you look at each. When it's time, there's often causality that plays a role, in the sense that if you have temporal data, then for example, if I ask you what is the probability for a given word next, then that will depend on what the words were before. Or if you look at the stock market, then typically the stock price will depend on the past, not on the future, right? And the weather the same, you know. Typically you have causality in the world, so that whatever happens at time t depends on what happened before. And so typically you would have an arrow that points to the right from the past to the future. And you see that in this processing, that this is kind of incorporated in this processing. Here's my input. This is a multi-layer recurrent neural network. And then you have all these hidden states, and then you have outputs. And the hidden states will have its own internal dynamics. So for example, if you track an object in a video, then the position of the object will depend on where it was before, and you can then extrapolate. You can have a model for how the car works, and that can govern the hidden states and their internal dynamics. And you can have very expressive models of how the state at time t evolves over time. One of the challenges is, if you phrase it like that, looks really nice, but obviously if you take an architecture like that, and that's kind of the key challenge in time series analysis, is you can have different steps in time, right? If I develop an architecture like this one, it would work to process an image, a video that has 7 frames, right? What if my video has 8 frames? Do I have to train a new network, or 9 frames or 10? Videos can have different lengths, different frames. And, once I set it up like that, the number of input images is fixed. And that's not good, right? I want something that can be flexibly adapted and applied to videos of arbitrary lengths, to time series of arbitrary length. And the question is, how can we do that? And how do we get this notion of time into it? So here's the basic structure of a recurrent neural network. So we have an input, xt, at time t. We have an output, h, at time t. And then we have what's called a hidden state, a. And as you can see, the hidden state depends both on the input at time t, and then this arrow basically says it also depends on its previous state. So the state at time t will be fed into the state for time t plus 1. And then you can, if you want to do it linearly, for example, you can say the state at time t is a linear combination of the state at time t minus 1 and the input at time t. And that would mimic somehow this structure, except that rather than having a fixed set of time steps, I basically define it like that, right? It encodes roughly the same idea, but the key is that these parameters will be independent of time, right? So they will have the same weights at every time. And here this is the previous hidden state, and that's the input at time t. And the idea is that I can learn these parameters and that they are assumed to be the same parameters for every time step. So one input per time step, one output per time step, and one hidden state per time step. By the way, here we ignore the nonlinearities. This is linear representation. In practice, you would have nonlinearities there as well. Activation functions, if you will. But what's nice is that you assume that these parameters, also the hidden state depends on the output ht depends on the hidden state at time t, and we assume the same parameters for each time step, and that way we can generalize to arbitrary length sequences. Now that sounds nice. In practice, you would often unroll this into something with t time steps here. But the idea is that you would have the same function for the hidden layers. And so the output at time 2 will depend on the input at time 2, but it will, through the hidden state, also depend on the previous inputs at time 1 and time 0, but through this hidden state A. And once you unroll them, you can treat them as feed-forward networks. And then it would look like that, with the idea being that these weights are shared. So you have the same W1 here, and the same W2, W3, and W4. And then you can do backpropagation learning, but this is often a little bit tricky if you do backprop through an RNN, because the longer you go back in time, the more you have to aggregate these derivatives. And then obviously you run into, you all know what we run into. What do we run into? Anyone? What's the usual problem? The vanishing gradients, they come back again, right? And that was a big issue for training recurrent neural networks, to the extent that for many years people believed, and I also believed, that recurrent neural networks didn't actually work, right? A bit sad, the powerful machinery to process time series. I think to date the time series analysis is a challenge. It got a lot better with two innovations that we'll talk about next, but processing time series was a big challenge. I guess it still is, otherwise we could predict the stock market and then who knows what would happen, right? But you know, there is the question: can we make machine learning work to predict time series? But one of the issues here is you have the vanishing gradient issue. If you do chain rule and you backprop through this network, then you get a lot of derivatives. Yet this is important. It is important to have that long-term dependency. For language processing, this is very important. If you read a book, then something you read early on will play a role for whatever happens later in the book. And you should keep track of what you have, and understanding a certain word doesn't even make sense unless you've seen the words before. And the question is, how can you capture that dependency? If you have a sentence that starts with, I moved to Germany, and yada yada, and then in the end you say, so I speak German fluently, you know, the, the whole causality only makes sense if someone kept track that you moved to Germany, right? And so you need to capture that dependency, between, this input and this output, basically. If you want to, for example, complete the sentence and say, what is the work that goes in here? The language model needs to be sufficiently powerful. And as you know, this is a big challenge even with the current language models out there. With every new version of GPT or other language models, the question is, what is their capacity? How much content can they take in so that they can make these connections? And obviously, the more dependencies they can capture, the more long-term dependencies they can capture, the more intelligent their output. And that's mainly the innovation we see from ChatGPT 3.0 to 3.5, 4.0, etc. So the question in processing time series is how to capture long-term dependencies. Now, let's forget the input for a moment. So as you see, the state at time t depends on the previous state and the input at time t. If we ignore that external input and just say the state at time t depends on the previous state, and that in turn depends on the previous state, so we have this theta c to the power of t times the initial state. And so we have these weights, and they are multiplied over and over again. And if we have 100 steps in the time series, then we have theta to the power of 100. And so this is the vanishing gradient that you see happening here. It's a big, big problem. And so if the weights are small, then this gets to 0. If the weights are large, then we have exploding gradients, which isn't much better, right? So there is a challenge. There is many ideas how to cope with that. For example, in time series analysis, so-called autoregressive models, there's whole books about it. I remember reading one of them years back. And what they often do is they process this. They take the weights and then compute what's called an eigenvalue decomposition. And then lambda has the eigenvalues. This is the matrix of eigenvectors, and lambda is a diagonal matrix with the eigenvalues. And the problem is, if one of them is above, larger than 1 or smaller than 1, the smaller than 1 they vanish, the larger than 1 make it explode. What you can do is you can take this decomposition and clamp all the eigenvalues to 1. And that way you get a little bit more stability. So this is one way to deal with it, and that way you can allow the cell to basically maintain its state. The eigenvalues are by construction clamped to 1, and that way you have less of an issue. But another way to tackle this is there is another issue, and that is the tangent hyperbolic. This, that we omitted so far. In addition, there is this activation function that we have. So we have the state, and then we have, and there is this activation, the tan h. And even if you clamp that to 1, you still have the issue with the activation functions that can saturate or can map things to 0. And so RNNs are prone to this vanishing or exploding gradient problem. And there wasn't really a solution up until one work that came about, and it's a work that actually was done here at TU Munich. It's called long short-term memory, or short LSTM. A work by Sepp Hochreiter and Jürgen Schmidhuber. I believe it's their most influential work. And the reason is that for many years the LSTM was the best way to process time series. The LSTM, I must admit, I find it a little bit complicated, so bear with me, I'm going to explain it. But it's a little bit engineered in my view, but it seems to work. At least for many years it was the best way to process time series in a deep learning setting. And the idea is that, the key idea is that they looked at this tangent hyperbolic and said, let's replace this with a somewhat more complicated structure, and that is this one. And you can see it is not somewhat more, it's significantly more complicated. And it's a little bit similar, though, to things we've talked about, for example, the ResNet, right? In that you have an information pipeline that processes information. And one idea here is that you only focus on deviations from identity. Meaning if nothing happens at that time, the state, the information is not touched. It's just passed through, basically. And then you have several locations where you have so-called gates. And this gate allows you to either remove information or feed in new information. And so you focus on this information transport. And so the key ingredients are that you have a cell that corresponds to basically the state of the system at a certain time. And then there's information coming in from the left and going out to the right, CT minus 1 and CT. And then we have these gates. And these little crosses, they are gates. And these are positions where the information flow is modulated. And it's modulated in several ways. So these gates allow you to remove or add information to the cell state. You have the sigmoid. This was the standard nonlinearity, I guess, for many years. And then you have the first gate is a gate that decides whether to erase the cell state or not. Right, so here comes in xt is the input at time t, h t minus 1 is the previous state, and then bf is a bias. And so here you see this linear combination of the input at time t, of the previous state and a bias, and then a sigmoidal applied to it, ft, and this is called the forget gate. And it basically tells if the output is 0, then it should forget the information it had. Or if the output is 1, then it basically keeps the information it has. Right? That's what's happening at this gate. So if f, the output of the sigmoid, is 0, then it kills whatever comes in here. And if not, it lets it go through. So this is called the forget gate. It just decides, do I keep that information that's coming in or do I kill it? And then there is a second gate that's called the input gate that allows to introduce new information to the information stream. So you see this is a cell that's kind of somewhat engineering, like designed to modulate information flow. I can kill the incoming information and I can add new information here in this gate. And how does that look? Well, it looks the same. It's a linear combination of the input of the previous state, but with different parameters, and of a bias. And we have 3 different parameters. So I have 3 parameters or parameter sets, one should say, for the forget gate, 3 parameter sets for the input gate. And they are all learnable, right? The whole point is that this is all, as always in the deep learning world, is differentiable. So I can backprop and learn all of these parameters that tell me what information to keep and what information to drop. And so this sigmoid here, this decides what information to update. And then if this is 1, then the information is updated according to tangent hyperbolic. and if it's 0, then it's not updated. Right? And the update is like an element-wise operation where I basically multiply, so the forget gate times the previous state, and then element-wise this I that is binary. If I add information, then I add this, or otherwise I don't. So that's the previous state and that's the current state, and in this way information is merged. I can keep the previous state and add something. I can kill the previous state and add something, and this is the two kind of ways how you can modulate the information stream. And then there is an output gate, so you can see the structure is somewhat complicated, and I should say that's one of the aspects I've never really liked about the LSTM, is that it's very complex structure. But this last output gate, it decides which values will be outputted. And the output is from this tangent hyperbolic from -1 to 1. And this is then output both as the system state on the top and the input to the next state cell here at the bottom. And so this is what the LSTM looks like in equations, right? The forget gate, the input gate, the output gate, and here the cell update in total, and the cell and the output. And all of these parameters are learned through backpropagation. There's lots of parameters for every cell, but they are trainable, sort of, right? Sorry, I realize the circles have shifted a little bit. They should be more to the left. This LSTM became really popular because it was able to cope with this vanishing gradient issue in recurrent neural networks, and it's one of the early works for time series processing. So here's this highway for the gradient flow, and the cell update, here's the cell update. What's important when coding an LSTM, we have to define the size of the hidden state. And what's important is these dimensions, much like in a ResNet. You remember in the ResNet, it was the same, that we just modulate the identity and check how do we deviate from an identity, and that only makes sense if the resolutions are compatible. So here, the input on the bottom from the previous stage should be the same size as this one. And the input should also be a 128 vector. Otherwise, you cannot fuse information because you are basically adding all of these informations to create a new one. Here, I'm actually showing the code for the LSTM. It's a little bit small. I suspect you may not be able to read it from back there. If not, you can find it on the slides. It's actually fairly straightforward. On the left, you have the forward pass. And here, for example, you have this AI, AF, AO, AG. Sorry, I should switch on my pointer so you see where I'm pointing. Here, you have this AIFOG. That is exactly, if we go back, this is these updates, FIOG here, right? This is the forward pass on the left. And then here you have the backprop on the right. And as always with backprop, you have to do, layer by layer backpropagate, and that's why you multiply all these terms with each other to step 4 to stay. So you have steps 1, 2, 3, 4, 5, and here and then the backprop obviously goes from right to left. So step 5, step 4, 3, 2, and then 1. So you can look at it and see it does make sense. And here you're piping everything through the sigmoids, these nonlinearities, right? that was the LSTM, and as I said, for many years it was the state of the art in time series analysis, became extremely popular up until the attention came into the world. The idea of attention is the core element of what's called a transformer. The idea there is, and the best analogy is that of language processing, where you have a sentence with a lot of words, and the words have meanings. And what you want in language processing, you want to find an embedding of a given word, or maybe part of a word, that encodes that meaning. The problem, though, is that words don't have meaning independent of context. The meaning of a word will always depend on the context, right? If I say, my little brown-haired girl went skiing yesterday, and then I say she, the word she, in that case, refers to a little brown-haired girl, right? But in a different context, the same word could refer to something completely different. For a machine to understand language, it has to understand what are all the meanings associated with that word. And these meanings are given by the other words in the sentence. They don't exist on their own, right? And so what you need is you need to somehow have information that flows between the different words of a sentence that enriches the embedding. So you have an embedding of the word she, probably something female, right? And then from the remaining words, typically before that word, they generate the context. They refine the embedding. It's not just something female, but it is a girl, it is small, it is brown-haired, whatever else, right? And this is quite common if you read a book and at some point you say he, well, the whole book tells you what he is, and then you will have tons of associations in chapter 5 about he, right? And there's many examples, right? If you read the word Harry, right? If you're reading a Harry Potter novel, then you know it's going to be Harry Potter most likely. Whereas if it's a novel about the English royalty, then it's probably Prince Harry or something, right? And so the meaning of words changes significantly based on context. And so you need something that makes information flow between words. And this is what attention is all about. So you have these attention modules that allow you to propagate information and to create embeddings and enrich these embeddings over time through processing the time series. And this is basically, and that's why it's called attention, because it says that some token, could be a word in language, attends to some other information from other words in the same sentence or in previous sentences. And this was made hugely popular by a paper that had the title, Attention is All You Need. If you look more closely into this, you'll find it's not quite true. There is a lot of, perceptrons or feed-forward networks that take up 2/3 of the capacity of the whole transformer network. So the attention is only 1/3 of what you need if you want to be precise. But I think they wanted to make a point that attention was important, and I think it is. This is one of the most influential works in the deep learning revolution. I think there were two massive breakthroughs. One was the convolutional networks on ImageNet, and the second generation of AI or machine learning or deep learning is attention. This is what really started to make things work on time series, on sequential data, on language, but it also swept over into other areas of data analysis that are not time series. And so all the time series approaches that you're familiar with today, the LLMs like ChatGPT, etc., they all use transformers and this concept of attention that is ingrained in the transformer. And it's a little bit complicated to visualize what attention is about and how it differs from convolution. Typically, in convolutions, you have information that, so the input to a neuron depends on, in a sliding window fashion, on the neighboring neurons in the previous layer, and you have a weight sharing, right? In a fully connected network, the input to a neuron in principle depends on all neurons of the previous layer, right? And in attention, it also depends on all neurons potentially, but with a weighting that tells you how important each neuron is to this or that, right? So you can imagine that the bottom might be, I don't know, a sentence in German, and this is the corresponding sentence in English, and then certain words will depend very much on certain other words. But in principle, that dependency could be very long range. And then you can have global attention where it can be, you know, any distance, and local attention where you only consider a certain window. And in practice, most existing approaches are local attention because you cannot make the window infinitely large for compute reasons. And this is one of the big challenges in transformers today, how to enlarge the attention window. But the idea is that with attention, you can capture long-range interactions like this one, where the meaning of some word will, you know, depend on, or the, you know, the causal, the meaningfulness of a term here will depend on much earlier terms. And as we discussed, RNNs have this issue that you have the vanishing gradient. You can capture that to some extent with this long short-term memory, but only for a certain limited time window. And the question is, how can I encode long-term dependency? And this is where this attention comes into play. And so I have a context that I add, and that context can depend on the current state and on previous states and on potentially very far states. And it tries to figure out what are the previous hidden states that are relevant or that mattered for this or that output, right? And it might say here for the output German in this sentence, that word Germany here matters. And if there was a different country up front, then the most meaningful word in the back would be different as well, right? And a lot of this development of attention and of transformers was driven by the following challenge. Given a sentence, a sequence of words, tell me what are the most likely next words, right? And this is how language generation is happening nowadays, is that you always, you know, generate new words based on the probability. You wouldn't necessarily always take the most probable one to give it a bit, otherwise the system would always generate exactly the same output, right? And as you may have noticed, ChatGPT doesn't always generate the same output. You give it twice the same question, it will give you two very different answers, right? And that's because there is a bit more randomness. You would take the most likely, but maybe also the second most or third most likely word to create a bit more randomness here. And but this challenge of predict the next word is what drove a lot of the developments in this field. And so here we have a decoder architecture. So we have, in addition to the hidden state that we had in the RNN, we have a decoder architecture, and the decoder takes as input the previous decoder's hidden state, and also the output, the previous output. And then we have a context, and that the context for the decoder time t+1 will depend on the previous hidden states. And that and this leads to what's called a transformer. That is the architecture that was advocated together with this concept of attention. And you can say it's the next revolution in deep learning. So the first one came about with convolutional networks, and in particular the paper AlexNet that we discussed, and a lot of follow-up networks. And then the second generation or revolution in deep learning came through this paper attention, where the main field where it was invented was NLP. But as I mentioned, from computer vision, the convolutional networks spread into many other areas. For example, protein prediction is a work that we did in 2016. And in the same vein, the attention swept over into other areas like image analysis. And they're so-called VITs, visual transformers, nowadays. And so that's interesting that even though the concept of transformers was first introduced for processing language and time series data, it turns out is very useful for processing other kinds of data. Why is that? Well, it is because this idea that the meaning of a word depends on the meaning of other words in the vicinity, that is also true for images, right? The meaning of a certain color pixel depends on the context. If I zoom in on a tennis ball and I ask you, what is that? You couldn't tell me, right? Could be a lemon. It's just round and yellow, right? But you know, if this is a picture of a refrigerator, then it's more likely a lemon. Whereas if it's a picture of a tennis court, it's actually more likely a tennis ball. And so exactly in the same way as with language, the meaning of a certain structure depends on the context. And the question is, how can we capture that context? And that's where attention comes in. And we'll talk more about attention in the next slides. So here is the basic architecture of a transformer. It looks rather simple, but note there is one little thing. There is an n times here. So this is a block, a multi-head attention block, and a feed-forward network, so a perceptron, if you will. These are combined, and then they are layered. And for example, in GPT 3.0, you would have 96 such blocks in a sequence, right? And then there's something called positional encoding here, and this multi-head attention that we'll talk about more. And this is done both on the input of your training data and on the output of your training data. So if it's language translation, the input would be a German sentence and the output would be an English sentence, for example. But depending on what application, input and output could vary. So for example, here output shifted right. If it's predict the next word, then basically the input would be the text up until then, and the output would be the next word, basically, or the whole sentence, including the next word, if you will. So let's look more closely at this architecture, because admittedly it's a little bit complex. Let me see, what time is it? I'm not going over time, am I? No, I still have 10 minutes. All right, very good. So one of the core blocks is this multi-head attention block. So let's look in more closely what that looks like. And this has three components, and this is the three key components of what's called an attention block. These are V, K, and Q. Q is what's called a query. K is called a key, and V is called a value. And these are a little bit abstract concepts, but let me try to explain them intuitively. Let's say you have a word, like in our example, she. the word she, and you want to know more about, you have an embedding, but you want to make that embedding more precise depending on the context. And so you will phrase a query to say, what does the word she refer to in the previous sentence? Girl, little girl, brown-haired little girl, right? And so each term, like the she, will have a query and ask, what are words in the sentence that relate to me? And how do they help refine my embedding, right? And that is the query. And then all the other words, they will have keys, and that those keys will tell you how much does that word respond to this query. For example, if it's the word she, then the word girl will be a very good match to the query, right? Because it will say, yes, I specify the she. And in turn, the girl, little, refers to the girl, so the girl will query what previous words refer to me and help me refine my embedding. And so each token, as it's called in the language processing, and you can think of it as words, but it could also be parts of words only, or multiple words, depending on how you want to do it. But let's just say a token is a word. Then each word can have queries, and then the others can have keys. And once the keys are identified to respond to a certain query, they come with a vector that allows to improve the embedding. For example, if the word is forest, and then I have green forest, right? Then green helps me to refine the forest, because then I know I'm talking not just about a gray forest in winter, but a green forest, right? But the word green, it will help to precise the embedding of forest, that it's not just a forest but a green forest, but ideally the vector that modifies forest to become more green is the same that would modify a different word, like green monster, for example, right? You can also make a monster green, much like, and ideally the vector that modulates the embedding to make it more greenish, that is the same vector that comes with the word green, right? And the idea is that every word is and it has an embedding in a very high dimensional space, and then you can move the embedding around based on the context. And the context is given by other words. So I have an embedding for forest, and then I can have a vector that points in the direction of making things greener, if you will. And I can add that both to the forest, but also to monster. And so this is the idea of this vector here. And this is the idea of having queries, keys, and vectors, right? And more specifically, the formula that is advocated in this attention paper is this one. The attention of QKV, that is the update I have to apply to the embedding. And that update depends on QKV in the following way. What you do here is you do a product, and this is actually, you see vector Q times K transpose. That is what's often called an outer product. It's basically the dot product of all queries with all keys. It's a matrix, and this is called the attention pattern. It's the multiplication of all keys with all possible queries. So you can imagine on the x-axis you have the keys, on the y-axis you have the queries, and you take all the dot products, and that gives you this attention pattern. It's a matrix. And it tells you how relevant is each key, each word in the sentence for each query, right? So I have the word girl. I want to know what are the words that relate to this word. What are the words that help me improve the embedding of this word, and then all the previous words, if they have some association with girl, they will say yes, I can help refine, and that is this product of Q times K. And then you do a softmax, and what that does is it's a column-wise softmax. So the formula looks easy, but the devil is in the detail. This is a column-wise softmax, so over all keys for a given query, such that this ends up being a normalized probability. right? So all the previous words can have a say on whether they have anything to do with the query. And then you want to normalize such that you can talk about probability. This is the most likely one, this is the least likely one, right? So for example, if there is a word she and previously there was girl, then girl is the most likely probably key to help precise the embedding of she. And so this is and you do the softmax to get the probability out. So this is normalized to 1. So if I add up the relevance of all keys, I get 1 in total, right? And there's this normalization over square root of dk. dk, this is the dimension of this space, and this is for numerical stability that they add this normalization term. And once you've identified the most likely keys in this way, this is a vector with all, then basically you get the corresponding value. That is the update vector. And so this product, this dot product of queries and keys, the way you can visualize it, you have one query that is, let's say, the word she in the sentence, and then you have a lot of other words that correspond to keys, and they can say how much do they relate to this word she, and if there is one of them being girl, then in this very high dimensional space, you have to think of this being in hundreds of dimensions, right? Then the two vectors are most closely aligned if they match, right? And so then the dot product will be very large. And so, for example, in this case, you might have a dot product where for this query, the dot product with K2 is very large, right? So as a probability distribution, you would have something that normalizes to 1. So the area under this curve would be 1, but the peak would be around 2. And the other ones are less important, right? And then you would predominantly update according to the vector V2 that improves the embedding of your token. And so the whole idea is how to update embeddings based on keys and queries and corresponding vectors that make things more girl-like or more green or whatever, right? But in a way that is all differentiable. Keep in mind that in the end we want to train all of these things. And then we have keys and queries and vectors, and all of these should be learned from example. And so based on this example, where the key 2 is clearly the most fitting one to this query, you would predominantly update based on the vector V2. Now, this is the basic idea of an attention head. What we have in transformers are multi-head attention. So that is, you don't have that only one attention map, but multiple, with multiple keys and queries and vectors. Because a given token will depend on many of the words, and there will be many different associations, possibly. And this is called a multi-head attention then. And as you can see here, this is then followed by a feed-forward network, so a perceptron, to model the outputs, to process the outputs of this attention map. So these outputs are processed in this feed-forward network. And as I mentioned, 2/3 of the parameters of like a model like GPT-3 actually go into these feed-forward networks. So there's a lot of capacity, and then this is layered n times, right? And in practice, let's say GPT-3, for example, has almost 100 such blocks. And as a result, the capacity of a network like GPT-3 is 175 billion parameters. So these are massive networks with tons of parameters. Whether you really need that many parameters, I don't know, but you know, the world is complex, and if you want to capture these nuances and the complexity of the world and the fact that both monsters and forests and other things can become green, but other things don't become green, right? The world is complex, and if the network is supposed to learn all of this knowledge, it has to be somewhere. In fact, I think from what I understand, the knowledge about the world is mostly encoded in these feed-forward networks. The fact that it actually knows something. You know, if you wanted to tell you something about Einstein or something, it will talk, and this will typically come in through these feed-forward networks that encode the knowledge about the world. And in the end, we have fully connected layers here. You have the same, so you have this multi-head attention and then a feed-forward structure. In practice, you see it here. In the output, you have a masked multi-head attention. Why would you have a masked multi-head attention? This is typically if you want to do next token prediction, then you want to make sure that the predicted token only depends on the previous tokens, not on the ones that come later. And you can assure that by masking the later ones out. The way you do that, by the way, in this query key value formula is that before applying the softmax, whatever you want to mask out, you put it to minus infinity. Why do you do that? I mean, in principle, you could first do the softmax and then later just put everything to 0. But once you do that, it's no longer normalized. The whole point of the softmax is to create a distribution that is normalized. And the question is, how can I mask out certain elements here such that it's still normalized? Well, I mask them out before applying the normalization. And I do that here by applying the softmax as this exponentiation. If I take minus infinity, then that will be mapped to 0 and the remaining structure will be normalized. So this is how the masking works in the. So you see there's a lot of details in there that are not seen here on the slide. But this is the idea of this masked attention. Let's see, what was I going to explain? And then what you do is you combine input and output of these multi-head attention blocks to make sure that they are consistent, and that gives you the training signal in a way, right? So you apply a softmax and then obtain an output probability. And that allows you to create a prediction, a projection and a prediction, and then you can use that as a training signal. There is one thing that is missing and that I haven't explained yet, and it's down here, the positional encoding. Let me explain that briefly. What is missing from self-attention? So the idea is, in this way, we can process words and how they influence each other, but what we haven't captured is the location where in the sentence a certain word appeared. Each word comes in with a key and a vector that responds to certain queries, right? But it doesn't say, I am at the beginning or at the end or in the middle of the sentence. And so you would like some encoding that tells you where you are. And that is this positional encoding. You see it here. And this is also a somewhat complicated idea. You want an encoding that tells you where in the sentence the word is, but you want something that you can add to the embedding, right? So you have an embedding that captures the meaning of a word, and that embedding changes through this processing of these attention blocks, right? So they modulate the embedding such that the meaning of the word she becomes more and more precise over the iterations. And that embedding should also contain somewhere the information where in the sentence the word is. And ideally, if you have the same location, you should have the same encoding of this location. But the values of this encoding shouldn't get too large. So I can't just say it's the first word, second word, third word, because if I have a sentence with 100 words, then the location position is all of a sudden the size of 100, and you want things to ideally be in the range of 0 to 1. And the way you can make that happen is that you basically take the position and you apply a lot of sinusoids, sine and cosine, much like a Fourier encoding, with multiple frequencies. So we take a certain frequency here, 2 to the power of I, and then we apply the cosine and the sine. So the way you can see that is that you have low frequency encodings with a low frequency where this sine and cosine basically tells you whether the word is more towards the beginning of the sentence or towards the end of the sentence, or the beginning of my attention window and the end of my attention window, no matter how large they are. And then the higher frequencies tell me if it's towards the beginning, is it more the second or the first or the third word, right? And so you have like a multi-frequency encoding that always has values between 0 and 1, but it tells you very precisely where a given word is in your sentence. And that is kind of added to this embedding. And this is what you have here. So you have an embedding that is basically includes the position of the word encoded in this Fourier representation. That's the final look. Let me say a few words. So the complexity of this is fairly high. You can see it here, different comparisons of complexity of these networks. Typically, the question is how large is the attention window? This is an important problem. A few tricks. They typically use the Atom optimizer to train. There's different learning rates that people use. Then they have a residual dropout. They have a label smoothing and what's called a checkpoint averaging. Maybe a few words. Why were they so successful? Because they outperformed everyone else on language tasks. Things like next token prediction, or things like language translation, English to German, English to French, etc., etc. And you see the black numbers are the best performing ones, and you see that transformer architectures do outperform the others, right? And there are now even better approaches than this one, but they're all based on transformers today. And so to summarize, transformers improved the state-of-the-art in machine translation. They launched a new era of deep learning in their core building block of all language models, BERT, GPT, ChatGPT, Llama, whatever. It's all transformer-based, right? And they eventually made it beyond time series analysis. This is a very influential work by a collaborator of mine, Alexei Dosovitsky and collaborators. It's called An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale. That is a paper that advocates the VIT, the vision transformers, and there's a lot of research happening, I should say now, in this field of transformers, both on vision transformers but also in language. For example, one big challenge is how to extend the attention span of these models, because that creates a big headache for compute. And so there are adaptive versions of attention that make it more scalable. So that's very much all about attention and about the transformers, and I'll see you next time. Thank you. Possibly we'll have a guest lecture next time. I'm still looking into options for that, but keep that in mind. There might be a guest lecture coming up.